A 55 kilograms boy initially at rest and at a height h equal 3 meters above the ground slides down a frictionless slide as shown in the adjacent figure. The bottom of the track is on the ground level, which is taken as a gravitational potential energy reference. So I've underlined the important given. So we have the bottom of the track also is on the ground level, taken as a reference, taken as gravitational potential reference. We have that the mass of the boy is 55 kilograms. He started moving from rest. The height at the beginning is 3 meters and the slide is frictionless. So calculate at the top of the slide the gravitational potential energy of the system, then the mechanical energy of the system. So GPE is mass times gravity times height. We're given the mass in kilograms. Gravity is 10 Newton per kilogram because the system is buoy earth, and the height with respect to the reference is 3 meters. So 1650 joules, because all the values are substituted in SI unit, so we obtain the energy in the SI unit. B, the mechanical energy of the system buoy earth. Mechanical energy at the top is equal to gravitational energy at the top, also plus the kinetic energy at the top. So gravitational potential energy is calculated in part 8650. Sorry, not in Newton, this is a joules. This should be joules. All right. And kinetic energy is 0 joule because he started moving from rest. The initial speed is 0 meter per second, and we know that kinetic energy is half times mass times v squared. So if v is 0, then the whole product will be 0. And thus the mechanical energy at the top is equal to 1650 joules. Not in Newton. Newton is the unit of force. Then, is the mechanical energy of the system buoy earth conserved along the slide? Justify. Yes, since the slide is frictionless. Determine the mechanical energy of the system buoy earth as he reaches the bottom of the slide. Mechanical energy at the bottom equal mechanical energy at the top. So it's equal to 1650, again a joules, not in Newton. Determine the kinetic energy of the boy as he reaches the bottom of the slide, then deduce his speed at this position. So mechanical energy at the bottom is equal to kinetic energy at the bottom plus gravitational potential energy at the bottom. But at the bottom means on the reference, so the height is equal to 0, and thus the gravitational potential energy is equal to 0 joules. So mechanical energy now at the bottom is equal to kinetic energy. We already found it to be 1650 joules. So now to find the speed, I continued here. Kinetic energy at P is half mvv squared. 1650 joules is equal to half times 55 times vb squared. So half times 55 is 27.5. That's why we divide both sides by 27.5. So we have 1650 divided by 27.5 equal vb squared. Then VB is radical 1650 divided by 27.5, and the value is 1650 divided by 27.5. Radical answer, it's equal to 7.74 meter per second. So this is 7.74 meter per second. All right. Now for the second exercise, a particle as of mass m equal 100 grams is launched at O with a speed of v0 equal 10 meters per second. As shown in the adjacent figure, the particle moves along the line OX, making an angle alpha equal 30 degrees with the horizontal. The horizontal plane passing through is the reference level of the gravitational potential energy, and the forces of friction are neglected. So is the mechanical energy of the system as Earth conserved? Yes, since the forces of friction are neglected. Calculate the mechanical energy of the system as Earth at position O. Mechanical energy at any position is equal to the sum of kinetic energy plus gravitational potential energy, half mv squared plus mgo squared. Don't forget to write the index here showing at which position you're calculating the kinetic energy and the gravitational potential energy and the mechanical energy and so on. So this index O, or when we write B, or when we write A, so you have to show at which position you are doing the calculation. Now here we say mechanical energy at O is equal kinetic energy at O plus GPE at O, half mv O squared plus mgho. As long as we are saying at position O, which is on the reference, so the height is 0, and thus the gravitational potential energy is 0. Alright, this is 0. So mechanical energy at O is half times 0.1 kilograms times 10 squared. We converted the grams into kilograms by dividing by 1000. We have to substitute the value in the SI unit. So half times 0.1 times 10 squared is 5 joules. Then they ask us, the particle stops at point B. So this means that VB is equal to 0 meter per second, such that OB, the distance covered by the particle, is 10 meter. Apply the conservation law of mechanical energy to calculate the height HB above the reference level. So to be able to solve the exercise, let's just first represent HB on the figure. We represented it perpendicular, starting from B perpendicular to the reference level. So they specified the method by which we have to calculate HB, so we have to stick to it. We cannot use another method as long as they specify the method that we have to use. So mechanical energy at O is equal to mechanical energy at B. Mechanical energy at O is calculated in the previous part and found to be 5 joules. So it's equal to kinetic energy at B plus GPE at B, half mvb squared mghb. But the kinetic energy at B is 0 because they told us that it stops at B, so VB is equal to 0 meter per second. So now 5 joules is equal to mgHb, 0.1 kilograms times 10 Newton per kilogram, or 10 meter per second squared, times HB. HB is equal to 5 meter because 0.1 times 10 is 1, so HB equal 5 meters.